Solar-driven water splitting. Sounds cool, right? And it is exactly what it says on the tin. In solar-driven water splitting, we are using solar energy from the sun to split water back into its component parts, which are hydrogen and oxygen. Now that sounds cool, but what is the use of that? We currently rely on coal, oil, and natural gas, which are each fossil fuels, and also nuclear power as our primary energy sources. Given that we have about 50 years of coal, 70 years of oil, 80 years of nuclear power, and 250 years of natural gas remaining, all of today's main sources of energy will be completely depleted within less than 10 generations. Rest assured, modern scientists have already started thinking of alternate sources of energy, such as solar energy, wind power, and wave power. But there is a slight problem. What happens when the sun goes down, or when it is not windy, or when the seas are calm? Our energy needs don't just stop here. Enter the hydrogen economy, where everything is powered by hydrogen. Our cars, trains, and lights can turn back on again. And what is even more amazing is that hydrogen is a clean energy source. But where does the hydrogen come from? Remember that water molecule? If only we could extract the hydrogen from there. After all, 71% of the Earth is made up of seawater. But splitting water requires energy. The sun is a great source of energy, delivering 3,850,000 exajoules of energy per year. At the moment, we use less than 1% of this. Wouldn't it be great if we could use the rest? And you guessed it. Those clever scientists have found a way. But first, let me tell you a secret. We are not the first to think of this. Nature has been doing water splitting for a very, very long time. In photosynthesis, plants essentially use sunlight to split water and combine this with carbon dioxide to produce glucose and oxygen. In order to perform artificial photosynthesis, we need something called a semiconducting photocatalyst, which can absorb the energy and cause a chain of reactions which produces hydrogen and oxygen from water. The semiconducting photocatalyst will be made up of two parts, the anode, where oxygen will be produced, and the cathode, where hydrogen will be produced. These semiconducting photocatalysts are usually combinations of metals which can be found in the D block of the periodic table. There are lots of chemical conditions which we must consider when choosing the right metal. However, most important is that it is cheap, abundant, and robust in order to allow us to scale this method up to a truly global scale. So how far have we got in terms of finding suitable photocatalysts? In 1972, Fukushima and Honda made the first discovery in water splitting by using titanium dioxide and platinum, which worked well under ultraviolet light, where the anode was made from titanium dioxide and the cathode was made from platinum. So why didn't we stop there? Firstly, platinum is expensive, and secondly, this combination only works under ultraviolet light, representing only 4% of the solar radiation that hits the Earth's surface. Instead, we want to find a photocatalyst that will enable us to use visible light as our energy source, just like plants do. Furthermore, visible light represents over 44% of the sun's radiation that hits the Earth's surface. Here are some examples of photocatalysts that we have found to work under the conditions that we require. There is still more research to be done to find the best one, but there is some evidence to suggest that we can make the system even more efficient by using techniques known as doping and the use of sacrificial reagents. So that's water splitting in a nutshell. I told you it is exactly what it says on the tin. I hope you can appreciate the simplicity of this exciting yet revolutionary future that will one day power our future.